You are lying in a dark room. The lights are off, the doors are closed, and the air is still. But the room is not empty. Right now, in this exact second, billions of invisible particles are pouring through the ceiling. They are passing through the wood, through the insulation, and down into the space where you rest. They are passing directly through your blankets, through your skin, through your blood vessels, and deep into your bones. They do not slow down. They leave absolutely no trace. They do not care that you are there. About 85% of all the matter in the universe is completely invisible. We can map where it is. We can calculate how much it weighs, but we have absolutely no idea what it is. Hello, and welcome to Sidereal. Tonight, we are tracking the unseen architecture of the cosmos. If you are joining us for the first time, please subscribe, leave a like, and tell us your location and the local time in the comments. There is one question underneath everything we will look at tonight. How did something that completely ignores our physical reality become the only reason we exist at all? By the time you fall asleep, you will understand the invisible ocean you are floating in. To understand the nature of this unseen material, we first have to understand the boundaries of our own bodies. Everything you have ever touched, seen, or interacted with is made of something physicists call baryonic matter. Baryons are the heavy particles that make up the nucleus of an atom, protons and neutrons. Orbiting around these heavy centers are electrons. Together, they form the physical substance of our world. When you place your hand flat against a wall and feel resistance, you are not actually touching solid matter. You are feeling a fundamental force of nature. The electrons in the atoms of your hand are coming close to the electrons in the atoms of the wall. Because they both carry a negative charge, they repel each other. This electromagnetic repulsion is what stops your hand from passing through the plaster. It is what gives the physical world its shape, its texture, and its solidity. The matter passing through your room tonight does not possess this property. It is non-baryonic. It is not made of protons. It is not made of neutrons. It does not have electrons. Most importantly, it completely lacks an electromagnetic charge. Because it has no charge, it cannot interact with the electromagnetic force. It cannot feel the repulsion of the atoms in your floorboards or the atoms in your skin. When one of these particles encounters a solid object, it does not crash into it. It simply drifts through the empty space between the nucleus and the electron shells of the atoms, moving exactly as it would in the deep vacuum of interstellar space. And there is a great deal of empty space inside an atom. If you were to enlarge a single atom until its nucleus was the size of a marble sitting on the center line of a football pitch, the nearest electron would be a tiny speck circling somewhere up in the back rows of the stadium. Everything in between is empty. The solidity you feel when you knock on a table is not the solidity of packed material. It is the force field of the electrons holding the line. To a particle that cannot feel that force field, the table is not an object. It is a sparse scattering of marbles in an enormous, empty hall, and the particle sails straight through the gaps without ever coming close to touching anything. Its lack of electromagnetic charge also means it has no relationship with light. Light is an electromagnetic wave. For an object to be visible, its atoms must be able to absorb or emit photons. When light hits a wooden table, the electrons in the wood absorb some of the energy and reflect the rest back to your eyes, giving you the color and the shape of the table. The unseen matter in your room cannot do this. It cannot emit a photon. It cannot reflect a photon. It cannot even cast a shadow. If you were to shine the most powerful laser ever built directly into a dense cloud of this material, the beam would pass straight through without scattering a single particle. Calling it dark matter is almost a misunderstanding. Dark implies a shadow, a presence that blocks the light. This matter is not dark. It is perfectly, absolutely transparent. The scale of this invisible ocean is difficult to hold in the mind. When we look up at the night sky, we see a universe that seems overwhelmingly full. We see the brilliant band of our own Milky Way galaxy. We see distant stars burning with the intensity of millions of nuclear furnaces. Through telescopes, we see glowing clouds of nebula gas, dense clusters of stellar nurseries, and other galaxies stretching out toward the edge of the observable universe. But all of it, every star, every planet, every moon, every comet, every speck of luminous dust, makes up only 5% of the universe. It is a rounding error. Roughly 68% of the universe is composed of dark energy, a completely different phenomenon that is actively stretching space apart. The remaining 27% of the total mass and energy is dark matter. When you remove dark energy from the equation and look only at the physical mass, the actual stuff that holds gravity, dark matter outnumbers normal matter by a ratio of more than 5-1. For decades, scientists tried to find a way out of this conclusion. They looked for ordinary explanations. Perhaps the missing mass was simply locked up in ordinary objects that we just could not see. They theorized the existence of massive compact halo objects. These would be things like brown dwarfs, which are failed stars too small to ignite nuclear fusion, or ancient dead stars that had completely cooled down and stopped emitting light. They even considered rogue planets wandering the deep space between stars, completely unlit by any sun. Astronomers gave these hidden objects a nickname, drawn from the first letters of that long description. They called them machos. The problem was how to find something that, by definition, gives off no light. The answer came in 1986 from a Polish-born astronomer named Bogdan Paczynski. Paczynski proposed an elegant trick. If a dark, heavy object passed directly between the Earth and a more distant background star, its gravity would bend and focus the light of that background star, acting like a brief, natural magnifying glass. For a few days or weeks, the background star would swell in brightness, then fade back to normal as the dark object drifted on. The dark object itself would remain invisible, but its gravity would leave a fingerprint in the light of the star behind it. This process is called microlensing. At the time Paczynski suggested it, the idea seemed almost impossible to use. To catch one of these alignments, you would have to monitor millions of stars, night after night, watching for the rare moment when one of them quietly brightened. In the early 1990s, several large international teams set out to do exactly that. One survey took the nickname directly and called itself the MACO project. Others ran in parallel from observatories in Chile and elsewhere. They photographed the dense star fields toward the center of our galaxy and toward our two small neighboring galaxies, the Magellanic Clouds, over and over again, comparing each night's image against the last, searching for the telltale brightening. The work was patient and largely thankless. Most nights, nothing happened. The stars simply burned at their fixed brightness, and the computers found nothing. And then, occasionally, they did find something. A star would brighten smoothly, peak, and fade, in the exact symmetric pattern that microlensing predicts. The dark objects were real. Brown dwarfs existed. Cold, dead stars existed. But when the surveys added up everything they had caught over years of monitoring, the numbers did not come close. The dark, ordinary objects in the halo of our galaxy could account for only a small fraction of the missing mass. There were simply not enough of them. Even if you counted every possible dead star, every faint brown dwarf, every wandering rogue planet, it fell far short of the weight that had to be there. We also know the missing mass is not antimatter. Antimatter is a mirror image of normal matter, carrying an opposite charge. When normal matter and antimatter touch, they instantly annihilate each other in a violent flash of pure energy, releasing a highly specific signature of gamma rays. If the invisible halos surrounding galaxies were made of antimatter, the borders where it touched normal gas clouds would be blazing with continuous gamma ray explosions. When we point our space telescopes at these regions, the sky is overwhelmingly quiet. There was one more candidate, and for a while it looked genuinely promising, because unlike all the others, it was a particle we already knew existed. The neutrino. Neutrinos are real, abundant, and ghostly in exactly the way dark matter needs to be. They carry no electric charge. They barely interact with ordinary matter at all. Trillions of them, produced in the heart of the sun, are passing through your body every second, and you have never felt a single one. They were already known to fill the universe in enormous numbers, left over from the early cosmos in quantities second only to the photons of light. On paper, they seemed like the obvious answer. Here was a particle that truly ignored the physical world, that we knew for certain was everywhere, that required no inventing at all. For a time in the 1970s and 80s, many physicists hoped the missing mass would simply turn out to be neutrinos. But the neutrino had a fatal flaw, and the flaw was speed. Neutrinos are almost weightless, and a nearly weightless particle born in the heat of the early universe, moves at very close to the speed of light. Physicists call this hot dark matter, not because of temperature in the everyday sense, but because the particles are moving so fast. And a universe whose dark matter moves that fast cannot build the structures we actually see. The whole role of dark matter was to gather quietly under gravity and carve out the deep valleys that ordinary matter would later fall into. A slow, heavy particle can do that. It pools, it settles, it clumps into the fine, branching filaments of the cosmic web. But a particle racing at nearly the speed of light cannot pool at all. It streams straight out of any small clump before gravity can hold onto it, smearing away exactly the small-scale detail that needs to survive. If the early universe had been filled with fast neutrinos, the cosmic web would have come out blurred and smooth, the smallest structures washed away, the galaxies forming far too late and in the wrong arrangement. When astronomers compared that prediction against the real sky, it did not match. The structure we see is sharp and finely detailed, which means the dark matter that built it had to be slow, cold, in the language of the field, heavy, sluggish, and patient. The neutrino was simply too quick. Whatever the dark matter is, it moves slowly, and that single fact rules out every particle we have so far confirmed to exist. So the invisible ocean is not dead stars. It is not brown dwarfs. It is not rogue planets. It is not antimatter. It is a completely new category of reality. It is a particle that was forged in the extreme heat of the very early universe, long before the first atoms were formed. It has existed since the beginning, outnumbering us, outweighing us, and quietly shaping the space we occupy. The Earth is moving through a vast halo of this material right now as it orbits the center of the Milky Way. The particles do not cluster in the center of the room or pile up on the floor. They are locked in their own immense, slow orbits around the galactic core. Some are falling in toward the center of the galaxy, others are moving out toward the fringes. They pass through our planet from every direction, completely unaware that the Earth is even here. The halo that surrounds our galaxy is not a thin shell or a flat disk. It is a vast, roughly spherical cloud, far larger than the bright spiral of stars it contains, swallowing the entire visible Milky Way and reaching out many times beyond its glowing edge. Our galaxy of hundreds of billions of stars sits at the center of this dark sphere like a few grains of glitter suspended in the middle of an enormous, invisible ball. The dark matter is thickest toward the center and thins gradually toward the edges, but it is everywhere, including here, in the unremarkable suburb of the galaxy where our sun happens to live. Physicists have estimated how much of it drifts through our own neighborhood, and the density is almost comically small by everyday standards. In a volume of space the size of your dark room tonight, there is perhaps the mass of a single small bacterium's worth of dark matter spread invisibly through the air, the walls, and your resting body. It is a whisper of substance, but space is so unimaginably large that those whispers, added up across the entire halo, outweigh every star in the galaxy several times over. And we are not sitting still inside this cloud. The sun, carrying the Earth and all the planets with it, is sweeping through the dark matter halo as it circles the galactic center. From our point of view, that means there is a steady stream of dark matter flowing past us, a faint and constant wind blowing through the solar system, through the planet, and through you, always coming from the direction we are traveling. You cannot feel it. It exerts no pressure, makes no sound, and stirs nothing. But it is the reason the deep underground experiments expect a faint yearly rhythm in any signal they might catch. As the Earth orbits the Sun, it spends half the year moving with that galactic wind and half the year moving against it. And a true dark matter detector should feel the stream blow a little harder, then a little softer, in time with the seasons, which leaves a strange and simple problem. If this ocean is completely invisible, and if it passes seamlessly through solid matter without leaving a trace, then how could anyone possibly know it is there? The answer is gravity. Gravity is the one language that both normal matter and dark matter share. Dark matter cannot touch us, cannot be seen, cannot be lit up, but it has weight, and weight bends the motion of everything around it. To find the ghost, astronomers had to learn to read its gravity, and before they could do that, they first had to be absolutely certain about how gravity and light were supposed to work together in the first place. In the late 19th and early 20th centuries, the science of astronomy was, at its core, a science of accounting. You looked through a telescope, you counted the light, and you calculated the mass. The assumption was absolute. What you see is what there is. Starlight was the ledger of the universe. If a region of space was blindingly bright, it meant there were many stars, which meant there was a great deal of physical weight pulling inward with gravity. If a region of space was dim, it meant there was very little mass. If a region was entirely black, it was empty. Astronomers built their entire understanding of the cosmos on this direct, unquestioned relationship between light and mass. They had good reason to be confident. The rules of gravity had been worked out with breathtaking precision by Isaac Newton and later refined by Albert Einstein. These rules dictated exactly how objects in space should move based on how heavy they were. We had tested them in our own solar system, and they worked flawlessly. The solar system runs on a principle known as Keplerian motion, named after the astronomer Johannes Kepler. In a Keplerian system, almost all of the mass is concentrated at the very center. For us, that is the Sunday. The Sun accounts for 99.8% of all the mass in the solar system. Because the gravity is so overwhelmingly strong near the center, planets that are close to the Sun have to move at extreme speeds just to stay in orbit and avoid being pulled into the fire. Mercury, the innermost planet, feels the full, violent drag of the Sun's gravity. To survive, Mercury races around the Sun at roughly 47 kilometers per second. As you move further out, the gravitational pull weakens following a strict mathematical rule called the inverse square law. If you double your distance from the Sun, the gravitational pull does not drop by half. It drops to 1/4. If you triple the distance, it drops to 1/9. Because the gravity gets rapidly weaker the further out you go, the outer planets must move much more slowly. If an outer planet moved as fast as Mercury, the weak gravity out there would not be strong enough to hold on to it, and the planet would simply break orbit and fly out into interstellar space. We see this perfectly demonstrated by Neptune. Far out in the freezing dark, billions of kilometers from the center, the Sun's gravity is merely a whisper. As a result, Neptune orbits at a leisurely pace of just over 5 kilometers per second. This rule is absolute. The closer you are to the central mass, the faster you orbit. The further you are from the central mass, the slower you orbit. The speed must drop as you move outward. Plot the orbital speeds of the planets on a graph, from Mercury out to Neptune, and you get a clean curve that rises near the Sun and then falls away as you move into the dark. Every astronomer of the era knew that curve by heart. The discovery that the spiral nebulae were distant galaxies did more than enlarge the universe. It transformed it from a still photograph into a moving thing. Once Edwin Hubble had established that the spirals were separate islands of stars at vast distances, he turned to measuring how they were moving, and he found something that unsettled everyone, himself included. Nearly every distant galaxy was rushing away from us, and the further away a galaxy was, the faster it was receding. The galaxies were not scattered through a fixed, eternal space. They were flying apart from one another in every direction. This was the first solid evidence that the universe is expanding, that space itself is stretching and carrying the galaxies along with it, like raisins set into a rising loaf of bread. And an expanding universe carries a startling implication when you run the film backward. If everything is flying apart now, then in the distant past everything must have been closer together, and further back still, packed into an unimaginably hot, dense beginning. The galaxies were the debris of an explosion that filled all of space at once. This is the idea that would later be called the Big Bang. It is the foundation that everything else in tonight's story rests upon, because to understand where the dark matter came from, we have to go back to that hot, dense beginning, to a moment long before any galaxy existed. But all of that lay in the future. For the astronomers first cataloguing the newly enlarged universe, the immediate task was simpler. They had a sky full of distant galaxies, and they wanted to know how much each one weighed. There was, in those years, a much larger and stranger question hanging over astronomy. Through their telescopes, observers could see faint, glowing spirals scattered across the sky, objects they called spiral nebulae. Nobody was certain what they were. One camp argued they were relatively small clouds of gas sitting inside our own Milky Way. which was assumed to contain the entire universe. The other camp argued something far more radical, that these spirals were separate galaxies in their own right, vast islands of stars floating at unthinkable distances, each one a Milky Way of its own. In 1920, the two sides met in Washington for what became known as the Great Debate, and neither side could prove its case. The instruments were not yet good enough to settle it. The tool that would settle it was not even a telescope. It was a relationship discovered a generation earlier by a woman named Henrietta Swan Leavitt, working at the Harvard College Observatory. In the early 1900s, the Harvard Observatory employed a group of women to do the painstaking work of measuring and cataloguing stars on photographic plates, a job considered tedious and clerical, and paid accordingly. The women were known, with the casual diminishment of the era, as computers, because computing was their function. Leavitt was assigned to study variable stars, the kind that brighten and dim on a regular cycle, in the two small companion galaxies of the Milky Way, the Magellanic Clouds. She examined thousands of them, by eye, on plate after plate, year after year. And in that vast, repetitive labor, she noticed something no one had ever seen, because no one else had looked at so many at once. The variable stars that took longer to complete their cycle of brightening and dimming were always, without fail, intrinsically brighter. The slower the pulse, the more light the star truly produced. The relationship was precise. It was a law. This was, quietly, the key to the entire universe, though almost no one realized it at first. Because the stars Leavitt studied were all clustered in the same distant cloud, all at roughly the same distance from Earth, the differences in their apparent brightness reflected real differences in the light they each gave off. She had found a way to read a star's true brightness directly from the rhythm of its pulse. And once you know how much light a star is truly producing, you can compare that to how bright it merely appears in the sky and calculate exactly how far away it must be. Leavitt had built a cosmic measuring stick. Any one of these pulsing stars, anywhere in the universe, could now reveal its distance, simply through the timing of its blinking. It was Leavitt's law that Edwin Hubble carried to Mount Wilson. When he found a pulsing variable in the Andromeda spiral, it was Leavitt's relationship that allowed him to convert its rhythm into a distance. Leavitt herself did not live to see most of what her discovery unleashed. She received little recognition in her lifetime, and the true scale of what she had made possible only became clear after her death. But every measurement of the size of the universe, every map of the cosmic web, every weighing of a distant galaxy's dark matter, traces back through Hubble to a quiet, careful woman counting blinking stars on glass plates in a room full of women who were called computers. It was settled a few years later by a single man working long, cold nights at the Mount Wilson Observatory above Los Angeles. His name was Edwin Hubble. Using the largest telescope in the world at the time, Hubble photographed the great spiral in Andromeda night after night, looking for a particular kind of star, a Cepheid variable, which brightens and dims on a regular, predictable cycle. The length of that cycle reveals exactly how much light the star is truly producing, which means that by comparing its true brightness to its apparent brightness, you can calculate precisely how far away it is. In 1923, on a photographic plate of Andromeda, Hubble found one. He had originally marked the spot on the plate with the letter N for a new star, a nova. Then he realized what he was actually looking at, crossed out the N, and wrote a single excited word beside it. Var, variable. That one star broke the universe open. Hubble's calculation placed the Andromeda spiral at a distance of nearly 1 million light-years, a figure later revised upward to 2.5 million. Either way, it sat impossibly far beyond the edge of the Milky Way. The spiral nebulae were not clouds inside our galaxy. They were other galaxies. In a single measurement, the known universe expanded from one galaxy to countless billions of them, and the faint spirals in the sky became the most distant objects anyone had ever measured. Now astronomers had a whole new population of objects to study, and they applied the only logic they had. They looked at a spiral galaxy and saw a structure that resembled the solar system, just scaled up by billions of times. In the center of the galaxy sat a massive, blindingly bright bulge of starlight. The density of light in the galactic core was overwhelming. Surrounding that bright core was a flat disk of stars, stretching out into thin, faint spiral arms that gradually faded into blackness. The conclusion seemed obvious. The light is concentrated in the center, therefore the mass is concentrated in the center. The light fades away at the edges, therefore the mass fades away at the edges. A spiral galaxy is just a giant solar system. The dense, bright core plays the role of the Sunday. The stars in the faint outer arms play the role of Neptune. The expectation was set in stone. If you measured the speed of the stars orbiting in a spiral galaxy, the stars near the bright center should be moving extremely fast, whipped around by the massive gravity of the core. As you measured stars further and further out along the spiral arms, their orbital speeds should smoothly and predictably drop off, getting slower and slower as the light faded into the dark. The galaxy's rotation curve should rise near the core, peak, and then fall away, exactly like the planets of the solar system. The astronomical community of the early 20th century was comfortable. They believed they had the tools to map reality. They had photographic plates to capture the light. They had the mathematics of Newton and Kepler to convert that light into gravity. They had a universe that appeared neat, orderly, and entirely visible. If a galaxy shone with a certain brightness, they could tell you exactly how much it weighed and exactly how fast its edges were spinning. They did not suspect that the visible light was lying to them. They did not know that the bright, beautiful spirals they were cataloguing were merely tiny luminous disks resting at the bottom of unimaginably massive, invisible structures. They believed the ledger was balanced. The ledger broke first in one of the most chaotic and violent environments in the entire observable universe. It broke in the Coma cluster. If you were to look toward the northern constellation of Coma Berenices, past the scattered stars of our own Milky Way, you would be looking toward a region of space roughly 320 million light-years from Earth. In this region, the universe has gathered an immense congregation of matter. The Coma cluster is a spherical swarm of more than 1,000 identified galaxies. These are not small, quiet structures. Many of them are massive elliptical galaxies, giant spheres of ancient yellow stars that have long since consumed their stellar nurseries. A galaxy cluster is not a static object. It is a deeply restless environment. The galaxies within the Coma cluster are bound together by their mutual gravity, but they are in constant, high-speed motion. They behave much like a swarm of bees trapped inside an invisible jar. They plunge toward the dense center of the cluster, accelerate as they pass through the gravitational gauntlet of the core, and are flung outward on long looping trajectories toward the edges, only to be pulled back in again. As they pass one another, their gravitational fields interact, stripping long tails of gas and stars from their outer edges. The space between the galaxies is filled with this torn, superheated gas, glowing faintly in X-rays. To understand the architecture of a cluster like Coma, an astronomer has to measure its velocity spread. You cannot simply look at a photograph and understand how the cluster works. A photograph is frozen. You have to measure how fast the individual galaxies are moving relative to the center of the swarm. By working out the average speed of the galaxies, you can determine how much gravitational glue is required to hold the entire structure together. If the galaxies are moving slowly, it takes very little mass to keep them bound. If the galaxies are moving with extreme violence, it takes an enormous amount of gravity to prevent them from tearing the cluster apart and flying out into the empty void between the galaxies. In 1933, the task of measuring the Coma cluster fell to a physicist named Fritz Zwicky, working at the California Institute of Technology. Zwicky was a brilliant, fiercely independent, and famously difficult man. He held a deep disdain for conventional thinking and frequently alienated his colleagues with his harsh criticisms and his unwavering belief in his own superiority. He once divided the people he disliked into categories of what he called spherical bastards, on the grounds that they were bastards when viewed from any possible angle. He was not a man who sought consensus. He was a man who hunted for anomalies, for the places where the standard picture of the universe cracked and failed. Over his career, that instinct served him astonishingly well. He coined the term supernova. He predicted the existence of neutron stars decades before they were found. He even suggested that galaxies could bend light, an idea we will return to later. He was right about a remarkable number of things, and almost nobody wanted to listen to him about any of them. Zwicky used the telescopes at the Mount Wilson Observatory. perched in the San Gabriel Mountains above Los Angeles. In the 1930s, astronomy was an intensely physical and solitary craft. To capture the faint light of the Coma cluster, Zwicky had to spend long, freezing nights inside the dark dome of the observatory. The work involved exposing glass photographic plates, coated with light-sensitive chemical emulsions, to the night sky for hours at a time. The observer sat in a small cage, suspended high above the concrete floor, manually nudging the massive steel telescope to compensate for the rotation of the Earth, keeping the distant galaxies perfectly centered on the glass. Zwicky was not only photographing the galaxies, he was capturing their spectra. He passed the incoming starlight through a prism, spreading it out into a band of color. Within that band, he looked for specific dark lines. These lines appear when the elements in the atmospheres of stars absorb particular wavelengths of light. Because the galaxies in the Coma cluster were moving, those dark lines did not sit in their normal positions. They were shifted. When a galaxy moves away from the observer, the light waves it emits are stretched, and the dark lines slide toward the red end of the spectrum. This is called redshift. By measuring exactly how far the lines had shifted on the glass plate, Zwicky could calculate the precise velocity of each galaxy. He selected several galaxies near the outer edges of the Coma cluster and measured their redshift. Then he applied a principle of classical mechanics known as the virial theorem. The virial theorem is a mathematical relationship between the energy of a system's movement and the energy of its gravity pulling inward. It is a balanced equation. If a cluster of galaxies has been sitting in space for billions of years without flying apart, the theorem states that its gravitational pull must be exactly strong enough to contain the speed of its moving parts. Zwicky approached the calculation methodically. First, he measured the luminous mass of the cluster. He added up the total starlight pouring out of the 1,000 galaxies. Using the Sun as his baseline, he converted all that light into physical weight. This gave him the total mass of the visible matter inside the Coma cluster. Then he looked at his velocity measurements. The numbers on his glass plates were extreme. The galaxies near the edge of the cluster were moving at velocities exceeding 1,000 kilometers per second. At 1,000 kilometers per second, a galaxy crosses the distance between the Earth and the Moon in less than 6 minutes. It is a speed born of overwhelming violence. When Zwicky fed these velocities into the virial theorem, the equation broke. The visible mass of the Coma cluster, the combined weight of all its billions of glowing stars, was nowhere near enough to contain that much motion. The gravity generated by the starlight was too weak by an enormous margin. By the rules of physics, the Coma cluster should not exist. The fast-moving galaxies should have overpowered the feeble gravitational grip of the visible stars and flown apart, scattering the cluster into the void long before human beings ever looked up at the sky. To keep the cluster intact, the virial theorem demanded a vast amount of additional gravity. Zwicky calculated the shortfall. To hold those fast-moving galaxies in their orbits, the Coma cluster needed roughly 400 times more mass than was visible in the telescope. The light was a lie. The starlight accounted for only a tiny fraction of the actual physical weight of the structure. The overwhelming majority of the Coma cluster was made of something that produced no light, absorbed no light, and left no trace on a photographic plate, yet held enough mass to trap 1,000 galaxies in a gravitational cage. That same year, Zwicky published his findings in a Swiss physics journal. He confronted the missing mass directly. He wrote that if his measurements were correct, they led to a surprising conclusion, that the cluster contained far more dark matter than luminous matter. He used the German phrase "dunkle Materie." It was the first time the term was applied to the unseen architecture of the cosmos. Zwicky laid the anomaly bare. He presented the mathematics. He presented the broken equation, and the astronomical community responded with near-total silence. For nearly 40 years, the discovery was effectively ignored. The universe of light was too comforting, and the picture of galaxies as giant Keplerian systems was too deeply rooted to be abandoned over a single strange cluster. Part of the silence was personal. Zwicky was difficult, and his ideas were often dismissed simply because he was the one presenting them. But part of the dismissal was reasonable. Measuring the velocity spread of a galaxy cluster is messy and uncertain work. It is hard to know whether a galaxy you are measuring truly belongs to the cluster, or whether it is a foreground object drifting past at a different distance. The calculations leaned on rough estimates of distance and on assumptions about the relationship between starlight and stellar mass that many astronomers felt were shaky. It was far easier to assume Zwicky had made an error somewhere, or that the missing mass was simply a vast cloud of ordinary gas, too dim for the telescopes of the day to detect. Zwicky was not, in fact, entirely alone, though he may never have fully appreciated it. 1 year earlier, in 1932, a Dutch astronomer named Jan Oort had been studying the motions of stars not across vast distant clusters but within our own Milky Way, close to home. Oort measured how quickly the stars near the Sun were bobbing up and down through the flat plane of the galaxy's disk, like horses rising and falling on a slow carousel. The speed of that bobbing depends on how much mass is pressing down from the surrounding disk, holding the stars in place. And when Oort added up all the mass he could actually account for, every visible star and cloud of gas in the neighborhood, it did not seem quite enough to explain how the stars were moving. There appeared to be more pulling on them than there was light to show for it. Oort's discrepancy was smaller and far more uncertain than Zwicky's, tangled up in difficult assumptions, and much of it would eventually be explained by ordinary matter that was simply hard to detect at the time. But the shape of the problem was the same. In two completely different settings, on two completely different scales, the very same quiet suggestion had surfaced in the very same decade. The visible matter was not enough. Something was missing from the ledger, and in both cases, the field was not yet ready to hear it. So the ghost in the Coma cluster was set aside. Astronomy returned to the ledger of visible light. The universe was assumed to be only what shone in the dark. The massive, invisible scaffolding holding the galaxies together remained unrecognized by the very people staring directly at it. The anomaly was filed in the archives, a peculiar mathematical curiosity from a difficult man. The field moved on to other questions: the expansion of the universe, the life cycles of stars, the violent physics of deep space. The comfortable certainty that mass could be measured by its glow stayed unbroken for a generation. It is worth pausing on what Zwicky had actually shown, because the scale of it is easy to miss. He had not found a small accounting error. He had not discovered that the cluster was 10% heavier than expected, or even twice as heavy. His calculations said the Coma cluster needed something like 400 times more mass than its starlight could supply. Imagine weighing a great ship by counting only the gulls perched on its deck, and concluding from the weight of the birds that the entire vessel beneath them must exist, vast and unseen and outweighing them many hundreds of times over. That is the size of the gap Zwicky had measured. The visible galaxies were the gulls. The ship was almost entirely dark. To look at that result and set it aside as a probable mistake took a particular kind of confidence in the comfortable picture of the universe. And for 40 years, the field had exactly that confidence. Zwicky did not live to be fully vindicated, but vindication came when Vera Rubin's flat rotation curves finally forced the community to accept the missing mass. Astronomers went back and looked again at the strange old paper from the Swiss journal and recognized that the difficult man had been standing at the answer decades before anyone else. Today, his name is attached to the discovery of dark matter in clusters, and the term he reached for, the dark matter itself, has become one of the central facts of modern science. The pattern would repeat throughout his career. Almost everything Zwicky was dismissed for in his lifetime, the neutron stars, the gravitational lensing, the missing mass, turned out to be real. When the certainty finally cracked for good, it did not crack in a violent, chaotic swarm of 1,000 galaxies. It cracked in the quiet, ordinary, beautifully ordinary spiral galaxies sitting peacefully in the dark. And it cracked in the hands of an astronomer who had deliberately gone looking for the most uncontroversial project she could find. In the late 1960s, the field of astrophysics was consumed by the discovery of quasars. Quasars are incredibly distant, blindingly bright objects sitting near the edges of the observable universe. When they were first detected, nobody understood what they were, and the debate around them was fierce, competitive, and loud. The astronomical community was locked in arguments at conferences and in the pages of journals, each researcher racing to be the first to explain the impossible physics of these distant beacons. Vera Rubin had no interest in that fight. Rubin was an astronomer who had spent much of her career being quietly excluded. As a young researcher, she had been told that certain observatories were effectively closed to women, that there were not even facilities for her to use. There is a story, which she told for decades, of arriving at the Palomar Observatory and discovering the building had no women's restroom at all. She is said to have cut a small skirt out of paper, stuck it onto the figure on the men's room door, and announced that now there was one. She had learned to do her best work away from the noise and the gatekeeping. By the late 1960s, she was at the Department of Terrestrial Magnetism at the Carnegie Institution of Washington, and she wanted, more than anything, a peaceful project, something foundational, something she could measure carefully, in the dark, without having to fight anyone for the right to be correct. So she chose to map the rotation curves of spiral galaxies, beginning with our nearest large galactic neighbor, the same Andromeda spiral that Hubble had used to crack open the universe 40 years earlier. A rotation curve is a simple, elegant graph. It plots the orbital speed of the material in a galaxy against its distance from the center. Rubin set out to measure how fast the gas and stars were orbiting around the core of Andromeda, working her way outward from the bright, dense center to the faintest edges of the spiral arms. It was a project of pure classical mechanics, and she expected it to confirm exactly what every astronomer already believed. She expected the rules of Keplerian motion, written large across a galaxy. Near the brilliant, heavy center, the stars should be whipping around at tremendous speed. As she moved outward, the velocity should slide smoothly downward, the graph rising near the core, peaking, and then falling away in a graceful curve as the visible light, and therefore the visible mass, thinned into blackness. It was a safe project, but it presented a serious technical barrier. To measure the drop-off at the edges, Rubin had to capture the velocity of stars at the extreme outer fringes of Andromeda, where the light reaching Earth is vanishingly faint. The old glass photographic plates, the kind Zwicky had used, were simply not sensitive enough. You could expose a plate to the outer edge of Andromeda for an entire night and end up with nothing but a few scattered, unreadable grains of silver. Fortunately, Rubin's colleague at the Carnegie Institution, Kent Ford, was a gifted instrument builder. He had recently finished developing a revolutionary new device, an image tube spectrograph. This instrument changed how astronomers caught light. Instead of waiting for photons to slowly build up a chemical stain on a glass plate, the image tube actively amplified the light as it arrived. When a faint photon of starlight entered the telescope and struck the front of the instrument, it hit a sensitive surface and knocked an electron loose. That electron was then accelerated by a high-voltage field, hurtling down a vacuum tube and slamming into a screen at the back, producing a flash of light far brighter than the original photon. By passing the light through several stages of this process, Ford's instrument could amplify faint starlight by a factor of 10. Suddenly, the invisible edges of galaxies were within reach. Rubin and Ford packed up the heavy, delicate instrument and traveled to the high observatories of the American Southwest. They worked from Lowell Observatory in Flagstaff, Arizona, and later from a large telescope at Kitt Peak, isolated on a mountain in the Arizona desert. The work of observational astronomy is quiet, cold, and deeply isolating. Night after night, Rubin and Ford sat in the freezing darkness of the dome. The only sound was the slow mechanical hum of the telescope turning to track the rotation of the Earth. They pointed the instrument at Andromeda, aiming at vast clouds of glowing, ionized hydrogen gas scattered through the galaxy's disk. Deep inside those clouds, newborn blue stars pour out ultraviolet radiation, stripping electrons from the surrounding hydrogen. When the electrons recombine with the atoms, they release a very specific shade of red light. Because that red glow is so distinct, it makes a perfect marker for measuring velocity. If a cloud was rotating toward Earth, its red line shifted slightly toward blue. If it was rotating away, the line shifted toward red. They gathered measurements from the bright inner disk. They moved the telescope outward and gathered measurements from the middle of the spiral arms. Then, using the full sensitivity of Ford's instrument, they pushed all the way out to the faint, isolated patches of glowing gas hanging in the dark far beyond the main body of the galaxy. At the end of each observing run, Rubin carried a box of small dark glass plates back to her office in Washington. Extracting the data was a process of slow, exacting precision. She used a device called a measuring engine. She placed each plate under a microscope, peered through the eyepiece at the faint glowing lines of the spectrum, and turned a fine screw to slide a set of mechanical crosshairs until they sat exactly on the center of the red line. She read the number off the dial, wrote it in a logbook, and moved to the next line. She spent hours in the quiet of her office, turning microscopic chemical stains into the physical velocity of a galaxy 2.5 million light-years away. When she had enough measurements, she began to plot the graph. She drew a horizontal axis for the distance from the center of Andromeda and a vertical axis for the orbital speed. She plotted the inner points first. As expected, the velocity rose sharply, the dense crowd of stars in the core whipping the inner gas clouds around at high speed. She moved outward and plotted the middle of the spiral arms. The curve stopped rising and began to flatten. That was slightly odd, but not impossible to explain. The disk was still fairly thick there. Then she plotted the extreme outer edges, the gas clouds far beyond where the starlight had any real presence, out to distances where the gravitational pull of the visible galaxy should have been almost nothing. She looked at the graph. The curve did not fall. Out at the dark, desolate edges of Andromeda, the velocity was a flat, horizontal line. The gas was not slowing down. It was orbiting the center of the galaxy at a steady 225 kilometers per second, just as fast as material far closer in. The mathematics of the solar system was simply broken. By Newton and Kepler, gas moving that fast, that far from the center, should have torn free of the galaxy's visible gravity long ago and dissolved into intergalactic space. Andromeda did not have enough luminous mass to hold onto its own outer edges. The stars and gas at the fringes should have escaped, and yet there they were, held in a tight, fast orbit. Rubin checked everything. She checked the measurements. She checked the calibration of the measuring engine. She checked the dark lines on the plates. The data was clean. The instrument had captured the velocities with undeniable precision. The flat rotation curve meant only one thing. The visible Andromeda galaxy, that beautiful glowing spiral of hundreds of billions of stars, was an illusion of scale. It was only the luminous center of a far larger structure. The vast majority of Andromeda's mass was invisible, spread through an enormous unseen spherical halo extending far beyond the edge of the starlight. As Rubin measured further out, the pull of the visible stars was indeed dropping away, but the pull of the invisible halo was rising to meet it, holding the orbital speed flat. Rubin and Ford published their Andromeda results in 1970. It was a careful, quiet paper. But in astronomy, a single anomaly in a single galaxy is easy to dismiss as a quirk of that one object. The community was intrigued, but not yet willing to abandon the ledger of light. Perhaps Andromeda had recently collided with another galaxy, and its outer regions were temporarily disturbed. Perhaps it was a fluke. Rubin understood this perfectly. She knew that to overturn a foundation of physics, she could not rely on a single galaxy. She had to prove that the broken mathematics was a universal law. She spent the next 10 years doing exactly that. She and Ford expanded their survey to a whole population of spiral galaxies, the kind with small central bulges and wide open arms. They measured massive spirals that dominated their corner of space. They measured tiny, faint spirals barely visible against the background. They measured galaxies that floated alone and galaxies packed tightly into groups. By 1980, they had compiled precise rotation curves for 21 different spiral galaxies. Every single one was flat. There was no drop-off. Not in the large galaxies, not in the small ones, not in the bright ones, not in the dim ones. In every galaxy they observed, the stars at the very edge were moving just as fast as the stars closer in. The flat rotation curve was not an anomaly. It was a basic property of the universe. The optical measurements had one natural limit. Rubin and Ford were tracking the glowing clouds of ionized hydrogen, and those clouds only extend so far before the visible disk of a galaxy fades into nothing. To push the measurement further out, into the truly empty dark beyond the last visible star, astronomers turned to a completely different kind of light. Cold, neutral hydrogen gas, the plain unlit hydrogen that fills the space between the stars, does not glow in ordinary colors. But it does quietly emit a faint radio signal at a single specific wavelength of about 21 centimeters, produced when the lone electron in a hydrogen atom flips its orientation. That radio whisper is far too faint for the eye, but a radio telescope can hear it. And crucially, the cold hydrogen reaches out far beyond the edge of the visible galaxy, trailing into the dark long after the starlight has given up. When radio astronomers measured the orbital speed of that distant, invisible gas in galaxy after galaxy, the curves stayed flat even further out than Rubin had been able to follow them. The gas at the very fringe, twice as far from the center as the last visible star, was still racing along at full speed, held in orbit by a gravity that no telescope could see the source of. The radio measurements and the optical measurements agreed completely, and together they extended the flat lines so far into the dark that there was no longer any reasonable way to explain them with visible matter alone. The astronomical community could no longer look away. The data was too clean, too broad, too consistent. The 40 years of silence that had followed Zwicky's chaotic cluster ended in the quiet, undeniable geometry of ordinary spirals. The conclusion was absolute. Every galaxy in the universe, our own Milky Way included, sits embedded deep inside a massive halo of dark matter. When you look at a photograph of a galaxy, you are not seeing the galaxy. You are seeing the glowing debris that has settled at the bottom of an invisible gravitational well. The stars and the planets are the 5% exception, a faint dusting of luminous material trapped inside a dark, heavy sphere that dwarfs them in both size and weight. There is a particular strangeness in applying this to our own galaxy, because we are not looking at it from the outside. We are living deep inside it, embedded in the very halo we are trying to measure. The Sun, with the Earth in tow, sits roughly halfway out from the center of the Milky Way, circling the galactic core once every 230 million years or so, moving at more than 200 kilometers per second. We have never completed even a fraction of a single orbit since the first humans appeared. And just as in Andromeda, the outer parts of our own galaxy are rotating too fast for the visible stars to hold them. Measuring this from the inside is genuinely difficult. We cannot rise above the galaxy and photograph it whole. We have to map it from within, tracking the motions of distant stars and gas clouds scattered around the disk, piecing together the structure of the halo that surrounds us the way someone trapped inside a vast, dark cathedral might try to map its shape by listening to echoes. The newest surveys have charted the positions and movements of more than 1 billion stars in our galaxy, and from that immense catalogue, astronomers have weighed the invisible halo that cradles us. The result is the same one Rubin found everywhere else. The Milky Way is mostly dark, the bright river of stars you can see on a clear night. The band of light that gave our galaxy its name is only the glowing sediment at the bottom of an enormous unseen sphere, and we are floating, right now, somewhere within it. Vera Rubin had gone looking for the quietest project she could find, and in the process, she had dismantled the visible universe. Years later, reflecting on the darkness that surrounded her clean, flat lines, she put it plainly. In a spiral galaxy, she noted, the ratio of dark matter to ordinary matter is around 10:1. That, she said, was probably also a fair estimate of the ratio of our ignorance to our knowledge. For all that she had done, the recognition was slow and incomplete. Vera Rubin's measurements became one of the foundations of modern cosmology, taught to every astronomy student in the world, cited in thousands of papers, woven into the standard picture of the universe. The work that overturned our understanding of what the cosmos is mostly made of is, by any reasonable measure, among the most consequential observational discoveries of the century. And yet she was never awarded a Nobel Prize. She continued observing, mentoring younger astronomers, and quietly pressing for women to be given access to the telescopes and the opportunities she had so often been denied. She remained, to the end, more interested in the next measurement than in the credit for the last one. When she reflected on her career, she tended to return not to the accolades, but to the darkness itself, to the simple, humbling fact that the universe had turned out to be overwhelmingly made of something no one could see, and that she had been the one to measure, with patient certainty, just how much of it there was. There was a deeper question hidden inside her flat lines, one that would push astronomers back to the very beginning of time. If these invisible halos wrap around every galaxy, holding each one together, then where did they come from? Did the dark matter gather slowly alongside the stars, as the galaxies formed? Or was it already there, waiting in the dark, long before the first star ever caught fire? To answer that, we have to travel back deep into the history of the cosmos, to a time when there were no stars, no galaxies, and no empty black void of space at all. In the first few 100,000 years after the birth of the universe, the cosmos was a radically different place. It was not a vacuum. It was a single, uninterrupted ocean of unimaginably hot plasma, a dense, glowing fog of subatomic particles. Protons, electrons, and photons of light were packed so tightly together that nothing could move without violently colliding into something else. In that extreme environment, ordinary baryonic matter, the material that would one day become our bodies, our planet, and our sun, was trapped in a state of total chaos. Gravity, as always, was trying to pull this normal matter together. It was trying to force the protons and electrons to clump up and begin building the dense knots that would eventually become stars. But gravity was fighting a losing battle against the light. Because the universe was so dense, the photons could not travel in straight lines. They ricocheted endlessly off the electrons, bouncing in every direction. This storm of trapped light exerted a powerful outward force called radiation pressure. Every time gravity managed to pull a small pocket of normal matter together, the pressure of the trapped radiation blasted it apart again. Normal matter was locked in an exhausting deadlock. It would begin to compress, then get blown outward, then begin to compress again, sending great pressure waves rolling through the plasma, like sound waves moving through an ocean. Ordinary matter was simply incapable of building anything. It was too hot, too reactive, too tangled up with the blinding light to settle down and form the foundations of a structured universe. If normal matter had been the only substance in the cosmos, the universe would have stayed a featureless, expanding cloud of hot gas for billions of years. No galaxies, no stars. But normal matter was not alone in the plasma. The invisible ocean was already there, and it was playing by an entirely different set of rules. Dark matter does not interact with light. It carries no charge. It does not emit light. It does not absorb light. And most importantly, it is completely immune to radiation pressure. While the normal matter was being battered apart by the trapped photons, the dark matter felt nothing. The storm of early light passed straight through it, as harmlessly and silently as the particles passing through the dark room where you are resting tonight. And because it was immune to the light, the dark matter was free to obey the only force it recognizes: gravity. Quietly, beneath the violent, glowing fog, the dark matter began to gather. Where there were tiny variations in the density of the invisible particles, gravity took hold. Small clumps pulled in more dark matter, grew heavier, and pulled harder still. The clumps stretched into long filaments, drawing material in from the surrounding space. Over millions of years, while normal matter was still trapped in its deadlock, the dark matter patiently assembled a colossal structure. The filaments crossed and tangled, forming heavy hubs where they met. Between them, immense empty voids were swept clean. This vast, branching structure is known today as the cosmic web, and it is the invisible scaffolding of everything. Dark matter clumped together first. It carved out deep gravitational valleys throughout space. It built the framework of the cosmos in complete darkness, constructing the cages long before there was anything to put inside them. It is hard to overstate the scale of the structure the dark matter built. The cosmic web is the largest pattern that exists in the universe, dwarfing individual galaxies as utterly as a galaxy dwarfs a single grain of sand. The filaments are strands of dark matter and gas stretching for hundreds of millions of light years, strung between dense hubs where great clusters of galaxies gather. Between the filaments lie the voids, vast and almost perfectly empty bubbles of space, some of them hundreds of millions of light years across, containing almost nothing at all. If you could pull back far enough to see the whole arrangement, the universe would not look like a random scattering of galaxies. It would look organic, almost biological, like a network of neurons, or the branching threads of a fungus, or soap bubbles pressed together, with the galaxies strung in bright beads along the edges of the dark, empty cells. Every galaxy sits somewhere on this web, at a junction, along a strand, or on the lonely shore of a void. Our own Milky Way is part of a small cluster, which hangs from a larger filament, which is part of a still vaster structure, sheets and walls of galaxies that are among the largest single objects ever identified, and the entire architecture, The filaments, the walls, the hubs, the empty voids between them, was laid down by the gravity of the dark matter in the first ages of the universe, a blueprint drawn in the dark that all the visible matter would later be forced to follow. Roughly 380,000 years after the beginning, the universe finally expanded and cooled enough for the environment to change. The temperature dropped. The chaotic plasma calmed. The protons and electrons slowed down enough to bind together at last, forming the first stable, electrically neutral atoms of hydrogen. With the electrons now locked away inside atoms, the photons of light were no longer ricocheting off them. The fog cleared in an instant. The radiation pressure evaporated. For the first time in the history of reality, light flew free, racing across the expanding universe in straight lines. That ancient light is still arriving. It has been traveling for nearly 14 billion years, stretched and cooled by the expansion of space until it is now a faint glow of microwaves, sitting just a few degrees above absolute zero, filling the entire sky in every direction. It is called the cosmic microwave background, and it is the oldest light there is, the afterglow of the universe's first transparent moment. We did not find it on purpose. In 1964, two engineers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for radio astronomy. They kept picking up a faint, persistent hiss, a background noise that came from every direction at all times and would not go away. They checked everything. They suspected the equipment. They even climbed inside the antenna and scrubbed out the droppings left by a pair of pigeons that had been roosting there, on the theory that the mess might be the source. The hiss remained. It turned out that the noise they could not get rid of was the cooling light of the early universe itself, washing over the Earth from all sides. They had stumbled directly into the afterglow of creation, and at first they had thought it was a problem with the wiring. That faint glow carries a hidden record. Frozen into it are the pressure waves that rolled through the early plasma, the deadlock between gravity and light, captured as tiny variations in temperature across the sky. Some patches of the ancient light are a fraction warmer, some a fraction cooler. Those patterns are the fingerprints of the matter that was beginning to gather, and when physicists like Jim Peebles worked out, in detail, what those patterns should look like, they found that the patterns only make sense if a large amount of invisible, pressure-immune matter was present at the time, quietly pulling things together, while the normal matter was still being thrown around by the light. The cosmic web that the dark matter had been building was written into the sky from the very beginning, and we can still read it. The detail of those frozen patterns tells us something more specific, something that reaches back to the neutrino's failure. The exact size and spacing of the warmer and cooler patches in the ancient light depend on precisely how the dark matter behaved, and the patterns only fit if the dark matter was cold, slow, and heavy, just as the structure of the modern sky demands. A universe built from fast, hot particles would have left a different and wrong imprint, smeared and faint. The afterglow of creation and the arrangement of the galaxies tell the same story from opposite ends of time, and both insist on the same kind of patient, sluggish, invisible matter. There is one more pattern hidden in that ancient light, and it has become one of the most powerful tools in all of cosmology. Remember the pressure waves, the great ripples that rolled outward through the early plasma as gravity and radiation fought each other. Each ripple was a spherical shell of compressed matter, expanding outward from a denser spot. When the universe suddenly cleared and the radiation pressure vanished, those expanding shells froze in place, leaving a faint preference across the entire universe for matter to gather in shells of one particular size. That size is enormous, around 500 million light-years across, and it is still imprinted on the distribution of galaxies today. Galaxies are very slightly more likely to be found that exact distance apart than any other. The effect is far too subtle to notice in any single patch of sky, but survey millions of galaxies and the preference rises out of the noise, a faint ring of enhanced clustering at a fixed, known distance. Cosmologists use it as a ruler, because we know how large that frozen ripple ought to be. We can measure how large it appears at different distances and chart precisely how the universe has expanded across billions of years. The sound waves of the infant cosmos have become a measuring tape laid across all of space and time. We can also test the whole picture in a way that would have been pure fantasy in Zwicky's day. We can build the universe inside a computer, Cosmologists take everything they believe about dark matter, a cold, slow, collisionless particle that feels only gravity, scatter it across a simulated volume of space in the same faint, lumpy pattern the ancient light reveals, and then let the simulated gravity run for a simulated 14 billion years. They do not tell the simulation what to produce. They simply let the dark matter gather under its own pull and watch what forms. What emerges, every single time, is a cosmic web. The same filaments, the same dense hubs, the same vast empty voids, branching across the simulated space in a structure that looks startlingly like the real distribution of galaxies we map in the actual sky. The largest of these simulations have traced the growth of structure all the way from the smooth early universe to the tangled web of the present day, and the match between the imaginary universe and the real one is close enough to be unsettling. Feed in a cold, invisible particle and nothing else, and you get our universe back out. That threefold agreement between the ancient light, the modern galaxy maps, and the simulated cosmos is one of the strongest reasons most physicists believe in something they have never once managed to touch. With the radiation pressure gone, the normal matter was finally released from its deadlock. The hydrogen gas could collapse under its own weight at last. But it did not collapse at random, and it did not build structures on its own. As the gas drifted through the newly clear universe, it felt the immense, pre-existing pull of the dark matter web. The gas had no choice. It poured into the deep gravitational valleys the dark matter had spent millions of years carving out, flowing along the invisible filaments and pooling in the massive hubs. Deep inside those invisible halos, the hydrogen compressed and heated, growing denser and hotter at the center, until it crossed the threshold for nuclear fusion. The first stars ignited, burning fiercely in the dark, lighting up the centers of the invisible spheres. For a long stretch before that first ignition, the universe had been completely dark. After the ancient light cooled and faded from view, and before any star had yet caught fire, there were no sources of light at all. Cosmologists call this stretch the Dark Ages, a span of many millions of years in which the universe was nothing but cooling hydrogen gas drifting in blackness, slowly gathering into the waiting dark matter wells. The timing of when that darkness finally ended, when the first stars blazed into being, was set entirely by the dark matter. The deeper and denser the invisible halos, the faster the gas within them could collapse and heat and ignite. Without the dark matter pulling the gas together, the first stars would have taken far longer to form, or might never have formed at all in the time available. The moment the cosmos first lit itself was scheduled by the unseen scaffolding. We are now, for the first time, able to look back almost to that moment. The newest and most powerful space telescopes are built to capture infrared light, the deeply stretched and reddened glow of the most distant objects in existence, whose light has been traveling toward us for almost the entire age of the universe. When these telescopes stare for days at a single dark patch of sky, they reveal faint smudges that are galaxies, as they existed in the first few 100 million years after the beginning, near the very end of the Dark Ages. Astronomers are studying these earliest galaxies to test the whole story, to check whether structure really did assemble as quickly as the dark matter picture predicts. The galaxies have turned out to be surprisingly bright and surprisingly mature for such an early time, which has prompted lively argument and careful rechecking, exactly the kind of pressure a good theory should be put under. But the broad shape holds. The first lights came on early, inside the dark halos, almost exactly as a universe built on cold, invisible matter would require. You exist tonight because the invisible matter went first. Every structure in the visible universe is a downstream consequence of that ancient, silent scaffolding. The iron in your blood, the calcium in your bones, the oxygen in your lungs, all of it was forged in the cores of stars. But those stars only had a place to form, only had the crushing gravity required to ignite, because a particle no one has ever seen built the furnace for them. The spinning galaxies, the glowing nebulae, the planets orbiting quiet suns, are the luminous debris that settled at the bottom of the dark matter wells. We are the brightly colored leaves caught in the deep, invisible currents of a much larger river. All of that rests on reading the gravity of something we cannot see, which raises the obvious challenge. If the cosmic web gives off no light, reflects no light, and casts no shadow, how could anyone possibly draw a map of it? The answer is that we map the invisible scaffolding by watching the way it bends the light of everything sitting behind it. To do that, we have to stop thinking of gravity as a simple pulling force and start thinking the way Albert Einstein taught us to think. In 1915, Einstein changed our understanding of gravity completely. Before him, gravity was imagined as an invisible tether, a mysterious force reaching instantly across empty space between two objects. Einstein showed that space is not an empty stage at all. Space and time are woven together into a single physical thing, a four-dimensional geometry that can be stretched, compressed, and curved. Mass tells that geometry how to bend, and the bend in the geometry tells everything else how to move. When a massive object sits in the universe, it does not just occupy space. It presses down on the fabric of space-time, creating a deep, curved depression around itself. The heavier the object, the deeper the valley. When another object, a planet or a comet, moves nearby, it is not being pulled by an invisible rope. It is simply rolling along the curved walls of the valley the heavier mass has made. And this curvature does not only steer objects with weight, it steers everything that travels through space, including light itself. Light always travels in a straight line, at a constant speed, but if the space the light is crossing is curved, then the straight line itself is bent. The light has no choice but to follow the contours of the geometry. This was not merely a theoretical claim. It was tested, dramatically, within a few years of Einstein proposing it, and the test made him famous across the world. Einstein's theory predicted that the Sun, being enormously massive, should bend the light of stars passing close to its edge, shifting their apparent positions by a tiny, precise amount. The problem is that the Sun is so blindingly bright that you can never normally see the stars near it. There is only one circumstance in which those stars become briefly visible, during a total eclipse, when the moon slides perfectly in front of the Sun and the sky goes dark in the middle of the day. In 1919, an English astronomer named Arthur Eddington led an expedition to observe exactly such an eclipse, traveling to a remote island off the coast of Africa to photograph the stars that appeared around the darkened Sunday. He then compared their positions to where those same stars sat in the night sky months later, when the Sun was elsewhere. The stars near the Sun had shifted by just the amount Einstein had predicted, as their light bent around the curved space near the Sun's great mass. When the result was announced, it confirmed that gravity really does bend light, that space really is curved by mass, and Einstein, almost overnight, became the most famous scientist alive. The bending of starlight had gone from an abstract equation to a measured fact, and once you know that mass bends light, and you know that the universe is full of enormous, invisible concentrations of mass, the path to weighing the dark matter by the bending of light becomes almost inevitable. Einstein himself worked out that a massive object could bend light enough to act like a lens, focusing the light of something behind it, but he doubted it would ever matter in practice. In 1936, prompted by letters from an amateur scientist named Rudi Mandl, who kept pushing him to publish the idea, Einstein wrote a short paper describing how one star could bend the light of another into a ring or a set of duplicate images. In the paper, he remarked, almost dismissively, that there was little chance of ever observing the effect. He thought the alignments would be far too rare and the bending far too slight. It was Fritz Zwicky, the same difficult man from the Coma cluster, who saw further. The very next year, in 1937, Zwicky pointed out that Einstein had been thinking too small. A single star was indeed a weak lens, but an entire galaxy, or a cluster of galaxies, with all their enormous hidden mass, would bend light powerfully, and the effect would be not only observable but genuinely useful. It could be used, he wrote, to weigh the unseen mass of the universe directly. He was right, but it took more than 40 years to prove it. In 1979, 3 astronomers, Dennis Walsh, Robert Carswell, and Ray Wayman, were studying what appeared to be 2 separate quasars sitting very close together in the sky. When they examined the light from the 2 objects, they found something impossible. The 2 quasars had identical spectra, identical fingerprints, the same redshift, the same chemical signature, down to the finest detail. 2 genuinely separate objects do not match that perfectly. What they were actually seeing was a single distant quasar, its light split into two images by the gravity of a galaxy sitting between it and the Earth. It was the first gravitational lens ever confirmed, exactly the effect Einstein had described and Zwicky had championed, finally caught in the act. Picture how it works. A beam of light leaves a brilliant quasar billions of light years away, near the edge of the observable universe, and begins its long journey toward Earth. For most of that journey, it crosses the empty voids between the cosmic web, through flat, undisturbed space, traveling in a perfectly straight line. But somewhere along the way, it passes a massive galaxy cluster. That cluster holds hundreds of visible galaxies and, far more importantly, the enormous invisible dark matter halo that binds it together. The weight of that dark matter has bent the surrounding space-time into a deep gravitational valley. The light from the distant quasar cannot pass straight through. It enters the curved valley and is forced to travel along the sloping walls, deflected, bending around the invisible obstacle. By the time it climbs out the far side and continues onto Earth, the original beam has been smeared and distorted, and when it finally reaches our telescopes, we do not see one clean image of the quasar. We see the work of a cosmic lens. Because the halo is roughly spherical and immense, the light is often split into several paths that bend around different sides of the dark matter and meet again at our telescope. We might look at a seemingly empty patch of sky and find four identical images of the same distant quasar, arranged around an invisible center, a pattern known as an Einstein cross. If the distant galaxy, the unseen halo, and the Earth all line up perfectly, the light bends equally around every side of the mass and arrives as a complete, unbroken circle of ghostly light hanging in the dark, an Einstein ring. More often, the alignment is slightly off, and the dark matter acts like a funhouse mirror, stretching and smearing the light of background galaxies into thin, sweeping arcs of blue and white curving around the invisible center of the cluster. This same bending does something else astronomers have learned to exploit. A massive cluster, with its deep well of dark matter, does not only distort the light of distant galaxies, it magnifies it. The curved space acts as a genuine lens, gathering and focusing the light of objects far behind the cluster, making them appear larger and brighter than they truly are. In effect, the dark matter provides a free, enormous telescope built by gravity, hanging in space. Astronomers deliberately point their instruments at the most massive clusters they can find, not to study the clusters themselves, but to peer through them, using the cluster's dark matter as a magnifying glass to see fainter and more distant objects than any human-built telescope could reach on its own. Some of the most remote galaxies ever observed, tiny and impossibly far, were only visible at all because a wall of dark matter in the foreground happened to be focusing their ancient light toward Earth. The invisible substance, which gives off no light of its own, has become one of our most powerful tools for collecting the light of others. We use the thing we cannot see to see the things we otherwise could not. Modern astronomers use those smeared arcs to do something that should be impossible. They use them to draw precise maps of a continent no one can see. When they study an image of a heavily lensed cluster, they stop trying to count starlight altogether. They ignore the bright, visible galaxies entirely and look only at the distortion of the background light. Using powerful computers, they measure exactly how far each distant arc has been stretched and exactly what angle the light has been deflected through. Then they run the equations of general relativity backward, asking how much mass it would take to bend the light by that precise amount. A severely stretched, violently distorted galaxy reveals a deep gravitational valley, a towering peak of dark matter. A light that is only gently warped reveals a shallow depression. Pixel by pixel, the astronomers build three-dimensional maps of the invisible universe. They can show where the dark matter rises into vast, unseen mountains and where it thins into empty valleys. They can trace the long, heavy filaments connecting one cluster to the next. We can chart the exact shape and texture of the unseen ocean, navigating entirely by the way it fractures the light of the stars sitting behind it. The dramatic lensing, the rings and crosses and great sweeping arcs, happens only in the young places where a massive cluster sits almost perfectly in front of a bright background object. But there is a gentler version of the effect taking place everywhere, all the time, across the entire sky, and learning to read it has given astronomers their widest view of the dark universe. Every distant galaxy we observe has had its light bent, very slightly, by all the dark matter lying between it and us. For any one galaxy, the distortion is far too small to notice. A faintly oval galaxy might be stretched by a fraction of a percent, an amount no telescope could distinguish from its natural shape. But photograph millions of background galaxies across a huge stretch of sky, and something appears in the statistics. The dark matter in front of them tends to stretch their images in subtly aligned directions, like a field of tall grass, all leaning the same way in the wind. By measuring the faint, shared lean of millions of galaxies at once, astronomers can reconstruct the dark matter spread across the foreground, even where there is no bright cluster to mark it. This technique, called weak lensing, turns the entire sky into a single enormous lens. Great surveys have used it to draw sprawling maps of the invisible matter across vast patches of the heavens, charting where the cosmic web rises and falls over billions of light years. And the maps show exactly what the simulations predict: a tangle of filaments, dense knots, and empty voids, the dark scaffolding laid bare, not in one cluster, but across great swaths of the universe at once. We have even traced the faint bridges of dark matter stretching between neighboring clusters, the invisible cables of the web strung directly between its hubs, detected purely through the gentle, collective bending of the light of the galaxies behind them. But a map has a limit. It tells you where the mass is, and how much of it there is. It does not tell you what the mass is made of. And here, a stubborn alternative survived for decades. Hydrogen is the most common element in the universe. A massive, diffuse cloud of ordinary hydrogen gas, if it were cold enough and sat far enough from any star, would be completely invisible to our telescopes. It would emit no light, reflect no light, and simply hang in the dark, carrying real weight. It would bend the light of background galaxies just as well as any exotic particle, perfectly mimicking the gravitational signature of dark matter. So how could anyone prove that the missing mass was a genuinely new kind of particle, and not just a vast cloud of cold, ordinary gas hidden in the black? To prove it, astronomers needed to physically pull the two substances apart and look at them separately. In a calm, settled place like the Andromeda galaxy or our own Milky Way, that is impossible. There, the dark matter halo and the ordinary gas are thoroughly mixed, occupying the same space, locked in stable equilibrium. You cannot separate them in a laboratory. You have to wait for the universe to build a centrifuge for you, and then go find it. You have to find a place where two colossal structures are being ripped apart by sheer physical violence. You have to find two enormous galaxy clusters caught in the middle of a head-on collision. In 2006, an astronomer named Doug Clow, working at the University of Arizona, used the Chandra X-ray Observatory to study exactly such a catastrophe. Chandra is not an ordinary telescope. It orbits high above the Earth, beyond our atmosphere, which blocks X-rays before they can reach the ground. Catching an X-ray is exceptionally hard. You cannot simply point a glass mirror at an X-ray source, because X-rays carry so much energy that they pass straight through ordinary glass or are swallowed by it. To focus them, you have to coax them. The mirrors inside Chandra are shaped like nested barrels, tapering gently toward the back. When an X-ray enters the telescope, it grazes the inside of the curved mirror at a very shallow angle, like a flat stone skipping across the surface of a still pond. It skips off one mirror, skips off a second, and is gently guided down to the detectors at the back. Chandra was built to watch the hottest, most violent phenomena in existence, and Clow and his team aimed it at a system known as the bullet cluster. The bullet cluster is not a single object. It is the site of an ongoing, slow-motion collision between two massive galaxy clusters. One is large and heavy, the other is somewhat smaller, and it has plunged straight through the core of the larger one. The collision has been unfolding for more than 150 million years. To understand what happens in such a collision, you have to look at the clusters in three separate layers, because each cluster is made of three very different things: the visible galaxies, the hot gas between them, and the dark matter. The first layer is the galaxies themselves. A cluster holds hundreds or thousands of individual galaxies, each one filled with billions of stars. When the two clusters slam together, you might expect the galaxies to crash and shatter in a great fiery wreck. but space is overwhelmingly empty. The distances between individual stars are so vast that when two galaxies pass through each other, the stars almost never touch. They slide past one another like two flocks of birds crossing the same patch of sky. The galaxies come through the collision largely undisturbed, coasting onward, carried by their immense momentum. The second layer is the normal matter, the baryonic gas. Between the galaxies in each cluster lie vast, sprawling clouds of hydrogen and helium. While the galaxies are mostly empty space, these gas clouds are huge and physically continuous. When the two clusters met, the gas clouds could not simply slide past one another. They collided like two walls of fluid, smashing together at thousands of kilometers per second. This is the layer Chandra was built to see. As the gas from the smaller cluster crashed into the gas of the larger one, the friction was tremendous. The gas was suddenly violently slowed. The energy of the collision converted instantly into heat, driving the temperature of the gas above 100 million degrees. Through Chandra's grazing mirrors, that superheated gas glowed fiercely in X-rays. Clow and his team saw a striking shape. The gas from the smaller cluster had been carved by the resistance of the larger cluster's gas into a sharp, bright form that looked exactly like the nose of a bullet pushing through the air, with a great bow shock of compressed gas rolling out ahead of it. The collision had stopped the normal matter in its tracks. Slowed by friction, the glowing gas from both clusters was pooling in the center of the wreck, caught in a hot, turbulent knot. There is a strange detail buried in this collision, one that astronomers are still chewing over. To carve that sharp bullet shape and drive the gas to such extreme temperatures, the smaller cluster must have torn through the larger one at a tremendous speed, faster, by some estimates, than seems easy to explain. In the standard picture of how the universe assembles its structures, clusters of galaxies fall toward one another gradually, pulled together over billions of years, and there is a rough upper limit to how fast two such enormous objects should be moving when they finally meet. The bullet cluster appears to push against that limit, the smaller cluster having plunged in faster than the simple models comfortably allow. It is not a contradiction that overturns anything, and there are reasonable ways to account for it, but it is the kind of loose thread that keeps astronomers cautious and curious, a reminder that even our cleanest evidence carries open questions inside it. The bullet cluster was also not the last of its kind. Once astronomers knew what to look for, the separated signature of a cosmic collision, they began to find other examples scattered across the sky. There are now several known systems where two clusters have smashed together and the gravity has visibly pulled apart from the glowing gas. Each one showing the same essential pattern, the hot baryonic gas trapped in the middle while the unseen mass coasts on ahead. Some of these collisions are caught at different angles, some at different stages of the crash, and a few are messier and harder to read than the original. But taken together, they form a small gallery of cosmic centrifuges, each one independently separating the visible from the invisible, each one telling the same story. The first such image was the most striking. It was no longer the only one. That left the third layer, the invisible scaffolding, and here was the test. If dark matter were nothing more than cold, ordinary gas that we could not see, then it would behave like the hot gas. It would crash into the gas of the opposing cluster, feel friction, slow down, and pile up in the center alongside the glowing X-ray material. To find out where the dark matter actually was, Clow's team mapped the gravity. They turned their optical telescopes to the faint, distant galaxies sitting far behind the wreck, and they looked for gravitational lensing, measuring the subtle distortions in that background light as it bent its way through the collision zone. Then they translated those bent arcs into a precise map of where the physical weight lay, and they laid the gravity map directly over the X-ray image. The mass was not in the middle. The deepest, heaviest gravitational valleys sat nowhere near the superheated gas. The computers revealed two towering, invisible mountains of mass, one well ahead of the glowing bullet on one side, one well ahead of the wreckage on the other. The visible galaxies, which had coasted freely through the empty space, sat neatly inside those invisible peaks. The collision had acted as a perfect cosmic centrifuge, cleanly separating the normal matter from the dark matter. When the clusters met, the gas had crashed, dragged, and slowed, trapping itself in the center. But the dark matter halos had not crashed at all. When the invisible halo of one cluster passed through the invisible halo of the other, it felt no friction whatsoever. It did not slow down. It sailed straight through the opposing mass as if nothing were there, carrying the overwhelming majority of each cluster's weight far ahead, away from the site of the impact. There was no longer any room to argue. The gravity, the real weight of the system, had physically separated from the ordinary gas. It could not be a cold cloud of hydrogen, because the cold hydrogen was sitting right there, glowing in X-rays in the center, while the mass had moved on without it. It could not be a simple error in the mathematics, because the mass and the gas were in two visibly different places on the same image. Reflecting on what the picture showed, Klaus said that a universe dominated by dark matter does sound preposterous, and that this was precisely why they had wanted to test whether the laws of gravity themselves might be at fault instead. The bullet cluster closed that door. The result, he said plainly, was direct proof that dark matter exists. It is a particle. It is heavy. It is ancient. And it moves through the universe entirely unhindered by the forces that govern our lives. We can see where it is, because we can see the deep valleys it carves into the geometry of space. We can watch it pass through the wreckage of a cosmic collision without leaving a single scratch. And it does not only ignore ordinary matter, it ignores itself. When billions of tons of dark matter slam into billions of tons of dark matter at immense cosmic speeds, there is no impact. There is no shock wave. There is no heat. The particles slide through one another with perfect transparency, feeling nothing but the slow, patient pull of their own gravity, which leaves a frustrating puzzle. We know it is a particle. We know it is pouring through the earth and through your body in vast numbers, every second of every night. So why, after all these years of trying, has no one ever caught a single one of them in a laboratory? The answer is that its interactions with the normal world are so vanishingly rare that catching one requires miles of solid rock and a kind of silence that does not exist anywhere on the surface of the Earth. The surface of our planet is, in physical terms, a deafening place. It does not feel that way, because our bodies evolved to ignore the constant barrage of high-energy radiation raining down from the sky. Every second, the upper atmosphere is struck by cosmic rays, protons and atomic nuclei hurled across deep space at nearly the speed of light by distant exploding stars and active black holes. When these cosmic rays hit the nitrogen and oxygen in our air, they shatter, producing a cascading shower of secondary particles. One of the most common of these is a particle called a muon. Muons are heavy, fast, and highly penetrating. Right now, as you rest in your dark room, roughly 1 muon is passing through an area the size of your hand every minute. They pass through the roof, through your body, and down into the soil. On top of that rain from the sky, the earth itself is faintly radioactive. The dirt, the concrete, the rocks, even the bananas in your kitchen all contain traces of slowly decaying elements like uranium, thorium, and a radioactive form of potassium. These constantly leak out low-level radiation and stray particles. Build a highly sensitive particle detector on the surface, switch it on, and it is immediately blinded. It records a chaotic storm of muons, gamma rays, and stray neutrons, drowning out everything else. It is like trying to hear a single snowflake land while standing next to a running jet engine. To hear the whisper of dark matter, physicists need absolute silence. And to find that silence, they have to abandon the surface entirely and bury themselves deep in solid rock. In the Black Hills of South Dakota, near the town of Lead, there is an opening in the earth, the entrance to the old Homestake gold mine, carved out of the dense rock over the course of a century. The gold is long gone, but the deep shafts remain, and the site is now the Sanford Underground Research Facility. Each working day, a team of physicists steps into a heavy steel cage. The iron doors slide shut, and the cage drops down the vertical shaft. The descent takes more than 10 minutes. The sunlight vanishes at once, replaced by the yellow glow of industrial lamps sliding past on the rough rock walls. The air grows warmer and more humid the deeper they go, heated by the warmth of the Earth's own crust. They pass the 1,000-foot level. They pass the 3,000-foot level. They grind to a halt at last at the 4,850-foot level, nearly a mile underground. At this depth, everything changes. The mile of dense rock overhead acts as an impenetrable shield. The muons raining down from the sky strike the mountain above and are absorbed by the stone. The cosmic radiation is blocked. The jet engine of the surface falls silent. Down here, the background radiation is reduced by a factor of 10 million. The physicists step out of the cage and walk through rough tunnels until they reach a set of heavy, sealed doors, and behind them, a pristine, brightly lit clean room built directly into the excavated rock. The air is heavily filtered. The walls are coated to keep out dust. This is the home of the Lux Zeppelin experiment, one of the most sensitive dark matter detectors ever built. The experiment is designed to hunt for a specific theoretical candidate for dark matter, a kind of particle physicists call a weakly interacting massive particle. The idea is that while dark matter is almost entirely collisionless, it might not be perfectly so. It feels no electromagnetic force, which is why it gives off no light and passes through walls. It feels gravity, but it might also feel one more of nature's fundamental forces, the weak nuclear force, a force that operates only across the tiniest of distances, deep inside the nucleus of an atom. If that is true, then there is a fantastically small chance that, if one of these particles passes directly through the exact center of an atom, it might just barely graze the nucleus. Not a violent crash. A microscopic, gentle nudge. The detector is built to catch that nudge. There was a deep reason physicists expected this particular kind of particle, and for a long time it felt almost too neat to be a coincidence. If you assume that dark matter is a heavy particle that feels the weak nuclear force, and you wind the clock back to the blazing heat of the early universe, where such particles would have been created in vast numbers and constantly destroying one another, you can calculate how many should survive, as the universe expands and cools, and the particles grow too sparse to find one another. The calculation produces a specific leftover amount, and that amount comes out remarkably close to the quantity of dark matter we actually measure in the universe today. A particle with roughly the mass and the feeble interactions this theory predicts would naturally leave behind just about the right amount of dark matter, with no careful adjustment required. The numbers simply line up on their own. Physicists called this striking coincidence the miracle, and for decades it was the single strongest reason to believe the dark matter particle would turn out to be exactly this kind of heavy, weakly interacting object. It tied dark matter to the known forces of nature. It suggested the particle ought to be detectable. It even hinted that the great particle accelerators might one day manufacture it directly. An entire generation of experiments, the deep xenon tanks among them, was built on the strength of that one elegant alignment of numbers. At its heart is a large titanium vessel, a cryostat, and inside it sits 7 tons of liquid xenon. Xenon is a noble gas, heavy, chemically inert, and difficult to obtain. To fill the tank, the scientists pulled xenon out of the atmosphere and put it through a punishing purification process, stripping out almost every trace of radioactive contamination until the purity was measured in parts per trillion. Any impurity left behind would emit its own faint radiation and create false signals that would ruin the silence. The purified xenon is chilled to around -100 degrees Celsius, becoming a dense, clear liquid. Xenon is used because it is an excellent scintillator. When a particle strikes a xenon atom, the atom absorbs the energy and releases a tiny flash of ultraviolet light. The trap works like this. The 7 tons of liquid xenon sit in the freezing dark of the titanium vessel, billions of dark matter particles, falling through the Earth on their slow galactic orbits, pass through the mile of rock overhead, through the ceiling of the cavern, through the titanium walls of the tank. The overwhelming majority drift straight through the empty space between the xenon atoms, feeling nothing, and continue on down into the core of the Earth. But the physicists wait for the microscopic exception, for the single particle that strikes a xenon nucleus head-on. If that happens, the nucleus recoils, and the recoil produces a first faint flash of light in the liquid. The recoil also knocks a few electrons loose. A strong electric field across the tank sweeps those electrons upward until they reach a thin layer of xenon gas at the top, where they produce a second, brighter flash. Lining the top and bottom of the tank are arrays of exquisitely sensitive devices able to detect a single photon of light in total darkness. They stare into the liquid, waiting for that exact 1 to 2 pattern, the faint flash followed by the brighter one, To make sure no stray radiation from the cavern walls triggers a false alarm, the entire titanium vessel is suspended inside a much larger outer tank holding 70,000 gallons of ultra-pure water. The water is a final, active shield. If a stray neutron from the surrounding rock makes it through, it flashes in the water, and the computers know to throw away any signal that appears inside the xenon at that same instant. The whole apparatus is a masterpiece of engineering, one of the quietest, most sensitive places in the entire solar system. The deep tanks are only one half of the hunt. If dark matter is a heavy particle that feels the weak nuclear force, then there should be a second way to find it, not by waiting for one to drift in from space, but by manufacturing one here on Earth. That is part of what the great particle accelerators were built to attempt. Near Geneva, on the border between Switzerland and France, physicists built the largest machine humanity has ever made, a ring of magnets buried in a tunnel running for many kilometers in a circle deep underground, called the Large Hadron Collider. Inside it, protons are accelerated to very nearly the speed of light and steered into head-on collisions, concentrating an enormous amount of energy into a single, fantastically small point in space. And energy, as Einstein taught us, can turn into matter. In the violence of those collisions, the energy can briefly condense into particles that do not normally exist in the world around us. Heavy and exotic particles that flash into being and then decay. The hope was that, every so often, a collision might forge a particle of dark matter directly, conjuring the invisible substance out of pure energy. A dark matter particle made this way could not be seen by the detectors. Of course, for the same reason it cannot be seen anywhere. It would feel no electromagnetic force and would slip out through the machine without leaving a trace. But physicists could catch it indirectly. They know exactly how much energy and momentum went into each collision, and the laws of physics demand that it all be accounted for afterward. If they add up everything that comes flying out of a collision and find that some energy and momentum have gone missing, vanished in a direction where no detector registered anything at all, that absence itself would be the fingerprint of an invisible particle escaping into the dark. So the physicists ran the collider for years, smashing protons together hundreds of millions of times every second, sifting through the debris of countless collisions, watching for that telltale missing energy. And once again, the result was the same as in the deep mines. They found the familiar particles of the known world, confirmed to extraordinary precision. They did not find the dark matter, the energy balanced. Nothing invisible escaped that they could clearly identify. There is a fourth way to hunt, and it points not down into the rock or inward at colliding protons, but outward, at the sky. If the dark matter particle is its own antiparticle, as some theories suggest, then in the densest regions of the universe, where dark matter is packed most tightly, two of them might very occasionally collide and annihilate each other, vanishing in a flash of ordinary energy, a burst of gamma rays, or a spray of familiar particles. We could never see the dark matter itself, but we might see those flashes, the faint exhaust of the invisible substance quietly destroying itself in the crowded dark. So astronomers point gamma-ray telescopes at the places where dark matter should be thickest. They look toward the crowded center of our own galaxy, where the halo is densest. They look at the small, faint satellite galaxies that orbit the Milky Way, which are known to be almost pure dark matter with very few stars to confuse the signal. They search for an excess glow of high-energy light that ordinary sources cannot explain. From time to time, a tantalizing hint appears, a faint surplus of gamma rays from the galactic center that some have argued could be the signature of annihilating dark matter. But the center of the galaxy is a violent, crowded place, full of ordinary objects that also produce gamma rays, and every promising hint so far has faded into the noise or found a more mundane explanation. The clean, unambiguous flash has not arrived. From 4 different directions now, the tanks deep underground, the magnets listening for the lightest particle, the great collider trying to manufacture the heaviest, and the telescopes watching the sky for its faint annihilation, the universe has returned the same quiet answer. We know it is there. We can weigh it across whole galaxies, and it refuses, again and again, to reveal itself in any laboratory we build. It is worth pausing on why so many people give their working lives to this search. descending into mines, tending magnets, sifting collision data, year after year, for a thing that may never appear. The reason is the size of the prize. Everything we currently understand about the particles that make up the physical world is contained in a framework physicists call the Standard Model, a beautifully precise accounting of the ordinary matter and forces we know. But the Standard Model has no place in it for dark matter. It describes the 5% and is silent about the rest. To detect a dark matter particle, even once, would be to find the first solid piece of a deeper layer of reality, a new fundamental constituent of the universe, lying entirely outside everything we have so far written down. It would not be the discovery of one more particle to add to a list. It would be the discovery that the list we have is radically incomplete, that the overwhelming majority of the matter in existence obeys rules we have not yet glimpsed. That is why the tanks are built larger and purer every decade, and why the silence, rather than ending the search, only sharpens it. The thing they are hunting is not a detail, it is most of the universe, and there is a strange beauty in the patience it demands, in the willingness of a person to spend a career maintaining a perfect, silent machine deep in the rock, knowing they may hand it to the next generation still empty, trusting that the answer, whenever it comes, will be worth every quiet year of waiting. The tank is filled, the doors are sealed, the sensors are switched on, and then the physicists simply wait. They wait for hundreds of days. The computers gather data continuously, recording the occasional stray gamma ray that pierces the shielding, the faint decay of the last few radioactive atoms in the tank, and sort patiently through all of it, discarding the known interactions, hunting for the one signature that would mean a dark matter particle had struck a nucleus. This is not the first such experiment, and it will not be the last. There have been xenon and argon tanks built deep beneath the mountains of Italy and inside the mines of Canada, each one larger, purer, and more sensitive than the last. For decades, scientists have been building these traps and refining them, and for decades, the result has been the same: silence. The sensors stare into the liquid, and the particle does not appear. The computers finish their sorting, strip away the background noise, and find nothing left behind. The tanks remain undisturbed by the invisible ocean pouring through them. There is one persistent exception, and it has caused 20 years of argument. Deep beneath a mountain in Italy, an experiment called Dharma has long claimed to see a real signal, not a single collision but a rhythm. As the Earth orbits the Sun, our planet moves with the galaxy's dark matter halo for half the year and against it for the other half, like a car driving into rain and then away from it. Dharma reports that the rate of faint flashes in its detector rises and falls on exactly that yearly cycle, which is precisely what a stream of dark matter should produce. The signal has persisted for 2 decades. The trouble is that no other experiment, using more sensitive equipment, has ever been able to reproduce it, and several should have by now, if the signal were really dark matter. So it sits there, unresolved, neither confirmed nor explained away, a single stubborn anomaly that the rest of the field cannot replicate and cannot quite dismiss. Apart from that one disputed rhythm, the great tanks stay silent. And every time an experiment runs for a year and finds nothing, the physicists do not give up. They adjust the mathematics. A null result tells them that if the particle exists, its chance of interacting with normal matter must be even smaller than they had thought. So they push the limit lower, build the next tank larger, make the xenon purer, dig a little deeper into the Earth, and hunt for a ghost that grows fainter and more elusive with every passing decade. It takes a strange kind of patience and a deep humility to descend into a mine every day to maintain a machine that may never, in your entire career, see the thing it was built to find. The long silence has done something to the field. It has not killed the idea of the weakly interacting particle, but it has loosened its grip and quietly pushed a second candidate forward into the light. This other particle could hardly be more different. It is called the axion, and where the weakly interacting particle is heavy and sluggish, the axion would be almost unimaginably light, far lighter even than the neutrino. It was not invented to explain dark matter at all. It first appeared in the 1970s as the solution to a completely separate and rather technical puzzle. about why one of nature's forces behaves with a perfect symmetry it has no obvious reason to obey. The mathematics that resolve that puzzle happen to predict a new particle, extraordinarily light and extraordinarily shy. And physicists soon realized that if such particles had been produced in the early universe, they would have been created in colossal numbers and would drift through the cosmos slowly and coldly, gathering under gravity in exactly the way the dark matter must. Two unrelated problems, one buried in the deep theory of forces and one in the weighing of galaxies, pointed to the same possible particle. Catching an axion would require a completely different kind of trap, because it would not nudge an atomic nucleus the way the heavier particle might. Instead, the theory predicts that inside a powerful magnetic field, an axion can occasionally convert into a single faint photon, a particle of radio energy at one precise frequency. So the hunt for the axion looks nothing like a tank of liquid xenon in a mine. It looks like a finely tuned metal chamber sitting inside an enormous magnet, slowly scanning across frequency after frequency, listening for the faint whisper of a radio signal that should not be there, the sound of dark matter quietly turning into light. The difficulty is that no one knows the exact frequency to listen for, so the experiments must sweep slowly across an immense range of possibilities, pausing at each step, straining to hear a signal fainter than almost anything ever measured. So far, like the great tanks, they have heard nothing, but the search has covered only a sliver of the possible range, and the axion remains very much alive, perhaps now the leading candidate, precisely because the heavier particle has stayed silent for so long. That long silence raises a harder possibility still, one the most honest physicists take seriously. What if the tanks are empty because there is nothing there to catch? What if the particle does not exist at all? When scientists confront a complete, persistent absence of evidence, they are forced back to the foundations of their own discipline. The entire idea of dark matter, the invisible scaffolding, the gravitational mountains, the particles raining through the Earth, rests on one specific pillar. It rests on our understanding of how gravity works. We say the dark matter is there because galaxies spin too fast and distant light bends too sharply. We measure the speed, we measure the bend, and we use the laws of gravity to calculate the mass that must be hiding. But if that mass cannot be found, after decade upon decade of looking, then it is fair to ask whether we have the laws of gravity right in the first place. Perhaps the universe is not filled with an invisible ocean. Perhaps we simply do not understand gravity at the largest scales. This is not a frivolous objection. We have tested the laws of gravity meticulously, but almost entirely in our own immediate neighborhood. We tested them in the solar system, where the sun's pull is overwhelmingly strong. We had never truly tested how gravity behaves across the vast, desolate emptiness of a galactic disk, where the central mass lies tens of thousands of light years away, and its pull has faded to almost nothing. In 1983, a physicist named Mordechai Milgrom, working at the Weizmann Institute in Israel, proposed that this untested regime was exactly where our assumptions had quietly failed. He looked at the flat rotation curves of Vera Rubin and Kent Ford, at the stars on the galactic edges refusing to slow down, and where most of the community chose to add invisible mass to balance the equation, Milgrom chose instead to change the equation. He called his idea modified Newtonian dynamics. Milgrom noticed something very specific in Rubin's galaxies. The rotation curves did not flatten at random. They flattened right at the point where the gravitational tug dropped below a certain, almost unimaginably tiny threshold. A star far out at the fringe of a galaxy experiences a pull from the center that is something like 100 billion times gentler than the gravity you feel standing on the floor tonight. It is an environment of extreme gravitational quiet, unlike anything in our solar system. Milgrom's proposal was that Newton's law of gravity is not actually universal. It is an excellent approximation in the high gravity world we know, but in that regime of extreme weakness, the rule shifts. Gravity stops fading according to Newton's strict formula and begins to fall off far more slowly, becoming stronger than Newton or Einstein would ever predict. The elegance of it was real. Apply Milgrom's modified mathematics to a spiral galaxy, and you no longer need an invisible halo of ghost particles at all. The visible starlight alone supplies exactly the right gravity. The outer stars race along because the rules themselves have changed in that ultra-weak regime, gripping them more tightly than classical physics allows. When Milgram published, his single adjustment correctly predicted the flat rotation curves of dozens of galaxies using nothing but their visible light. For many physicists, this was deeply attractive. Physics has a long love affair with simplicity, and inventing an entirely new, undetectable particle to patch an equation felt clumsy, while quietly correcting a law of nature to match what the sky was actually doing felt clean. Milgram's theory forced the rest of the field to defend the invisible ocean rather than simply assume it. It demanded that they prove dark matter was a real substance and not just a placeholder for a broken understanding of gravity. For years, the contest was genuinely close. Then came the bullet cluster. Recall what that collision revealed. The ordinary gas, slowed by friction, pooled in the center, while the gravity, the real weight, sat far ahead in two clean peaks, where the dark matter had sailed through untouched. For modified gravity, this is a serious problem. If there is no dark matter, then all the gravity must be generated by the visible matter. And in a cluster, the great bulk of the visible matter is that hot gas in the middle. So the deepest gravitational valleys should sit directly on top of the pooled gas. The gravity should follow the mass you can see, but it did not. The gravity had separated from the gas and moved on ahead with something invisible. Modified gravity can change how strong a pull is, but it struggles badly to explain how the source of the pull physically detached from the only visible matter present. To rescue the theory in the bullet cluster, its defenders generally have to assume large amounts of some other undetected matter after all, which quietly gives back much of the simplicity that made the idea appealing in the first place. The early universe poses a second hard challenge. The faint patterns frozen into the cosmic microwave background, the fingerprints of those ancient pressure waves, have a very particular size and spacing. The dark matter picture, with its pressure-immune particle quietly gathering while the light still raged, predicts those patterns with stunning precision. Modified gravity has struggled to reproduce that same success without heavy and complicated additions. Researchers have built relativistic versions of the theory to try, most notably the physicist Jacob Bekenstein, who in 2004 constructed a full mathematical framework to extend Milgram's idea into Einstein's universe. These versions are real, serious physics, but they have not matched the clean, predictive power of dark matter across every test at once. And yet the debate is not over, and it should not be. There are rigorous, careful physicists who keep refining modified gravity, and they are right too. They point out genuine weaknesses in the dark matter models, especially in how dark matter is predicted to behave in the dense centers of small galaxies, where the simulations and the observations do not always agree. There are even collisions that seem to point the other way. One smashed cluster, sometimes nicknamed a cosmic train wreck, appears at first glance to show dark matter sitting with the gas rather than ahead of it, the opposite of the bullet cluster, and no one has fully explained it. There is also a strange and revealing kind of evidence that cuts the other way, against modified gravity, and it comes from galaxies that appear to hold almost no dark matter at all. If the flat rotation curves were truly caused by a change in the law of gravity, then that change would apply everywhere, to every galaxy without exception, because a law of nature cannot be switched off in one place and on in another. Every galaxy of a given size should show the same excess pull. But in recent years, astronomers have found a handful of faint, diffuse galaxies that seem to behave almost exactly as ordinary gravity, with no hidden mass, would predict. Their stars move slowly. Their outer regions are not racing. They look like galaxies made of nothing but the matter you can actually see. Under modified gravity, this should be impossible, because the modified law would force them to behave like all the others. But under the dark matter picture, it makes perfect sense, because dark matter is a substance, and a substance can be abundant in one galaxy and largely absent from another. Perhaps these unusual galaxies were stripped of their dark matter long ago in some violent encounter, leaving only the visible stars behind. A galaxy that has lost its dark matter is a perfectly natural idea, if dark matter is a thing. It is a contradiction, if dark matter is only a rule. The very existence of these stripped, naked galaxies is some of the cleanest evidence that the missing mass is a real, separable substance, and not a flaw in our equations. The argument now reaches all the way down to pairs of individual stars. If the law of gravity truly changes wherever the pull becomes extremely weak, then it should change not only at the edges of galaxies, but anywhere the pull falls that low, including between two stars orbiting each other at a great distance, far out in the quiet of our own galaxy. Astronomers have begun measuring these wide, stellar pairs with extraordinary precision, watching how they swing around each other in a regime of gravity almost as gentle as the galactic fringe. Here, the two pictures make different predictions. Ordinary gravity says the stars should move one way. Modified gravity says they should move slightly faster. The measurements are difficult, and the results are still argued over, with different teams drawing different conclusions from the same kind of data, but the test is real, and it is being run right now. The question of the missing mass, which began with a difficult man weighing a swarm of distant galaxies, has narrowed all the way down to the precise dance of two stars circling each other in the dark. These dissenters provide a necessary friction. They keep the field honest, and they make sure the search for the missing mass never hardens into dogma. But when the majority of astronomers weigh everything together, the deep valleys of the cosmic web, the cleanly separated mass of colliding clusters, and the exact geometry of the early universe's light, they reach the same conclusion. They accept the strange, unsatisfying reality of a particle no one has caught over the clean elegance of a rewritten law. The evidence for the substance is simply broader than the evidence for the modification. There is one more idea worth holding in mind as we drift toward the edge of what is known, because it sits in the space between the two great camps and may yet turn out to matter. All this time we have spoken of dark matter as a single simple particle that feels nothing but gravity, sliding through everything, including itself, without the faintest interaction. That assumption fits almost all the evidence beautifully, but some physicists have begun to wonder whether the dark matter might be slightly richer than that. What if dark matter is not one lonely particle, but a whole hidden family of them, with forces of their own that we have no way of feeling? Our entire luminous world, all the chemistry and light and structure of ordinary matter, arises because normal particles can push and pull on one another through forces beyond gravity. Perhaps the dark sector has its own version of that, its own forces, invisible to us, through which dark matter particles can interact with each other while still ignoring everything we are made of. This idea is sometimes called self-interacting dark matter, and it is appealing because it might quietly fix the few places where the simplest models stumble, the dense centers of small galaxies, where the predicted pileup of dark matter does not quite match what astronomers see. A dark matter that can gently bump against itself would smooth out those centers in just the right way. We have no evidence yet that any such hidden force exists, but it is a reminder that the invisible ocean may not be as featureless as we assume, that there could be an entire shadow world of particles and forces woven through our own, touching us only through the faint, patient pull of gravity, and otherwise as silent and unreachable as everything else in the dark. So neither the deep tanks nor the alternative theories have given us a final answer. The particle has not been caught. The law has not been convincingly rewritten, which leaves us, at the end of the night, almost exactly where we began. A tiny, luminous exception, floating in an invisible ocean we still cannot touch. Step back from the galactic edge. Step back from the wreckage of colliding clusters, and from the deep, silent rock of the underground mines. Return to the physical space you are occupying right now. Listen to the quiet of the room. Feel the weight of the mattress holding up your body. Feel the texture of the fabric against your skin. Notice the slow expansion and contraction of your lungs as you draw the air in and let it go. Every part of this experience is governed by the rules of ordinary baryonic matter. The mattress holds you up because the electrons in its fibers are pushing back against the electrons in your skin. The air fills your lungs because the pressure of the atmosphere drives oxygen down your airway, where the iron in your blood binds to it. The walls stand because the molecular bonds of the wood and plaster are locked in stable geometric structures. This is the universe we understand. A universe of friction, of collision, of chemistry, and of light. It feels complete. When we look outward, we see the same ordinary matter scaled up to magnificent proportions. The heavy tectonic plates of the Earth grinding upward into mountain ranges. The deep oceans circulating their warmth around the globe. The storms of Jupiter. The icy rings of Saturn. The steady nuclear fire of the Sunday beyond the solar system. The glowing clouds of the Orion Nebula, where hydrogen is collapsing into new blue stars. the ancient yellow light of the Milky Way's core, hundreds of billions of galaxies scattered across the observable universe. A tapestry of light stretched across distances that break the human capacity for scale. It is a staggering inventory of physical reality. And all of it, the mattress, the air, the earth, the oceans, the sun, the nebulae, the hundreds of billions of spinning galaxies, amounts to almost nothing, 5% of the cosmos. The rest is the dark, silent ocean. That ocean was here first. Before the early plasma cooled, before the first atoms of hydrogen could form, the dark matter was already at work, gathering in the dark, sliding together under its own gravity, carving out the deep valleys that would become the cosmic web. When the ordinary matter was finally released, it had no choice but to fall into the traps already laid for it. The hydrogen poured into the invisible halos, pooled, compressed, and caught fire. The galaxies did not create the dark matter. The dark matter created the conditions for the galaxies. We are the luminous debris clinging to the bottom of those vast, unseen structures, the brightly colored growth on the surface of a bedrock no one has ever seen. The Earth is moving along its orbit at 30 kilometers per second. The entire solar system is sweeping around the center of the Milky Way at 230 kilometers per second. And all the while, we are plunging headlong through the great spherical halo of dark matter that surrounds our galaxy. It does not push against us. It does not slow us down. It simply lets us pass. The way it lets the light pass, the way it lets each other pass. About 85% of the matter in the universe is completely invisible. Right now, in this exact second, billions of its particles are moving through your body, through the bed, through the floor, through the dark room around you, and out the other side. They leave nothing behind. We have mapped where this ocean lies. We have weighed it with the bending of distant light. We have watched it pass clean through the wreckage of colliding worlds. And after all of that, standing here at the edge of everything we have learned, we still cannot say what it is. Good night.